So exponential functions. So these are what we're required to do by the SOLs. Be able to convert between logarithmic and exponentials. Okay, we can't do that one today because we do the logarithmic next time. Recognize the graphs of exponential parent functions, which we'll do that today. Transform the graphs, meaning shift them around by adding and subtracting and multiplying, all that. Same as we've done before. Describe restricted domains and ranges. And it turns out exponentials have a restricted range. And find the equations of asymptotes. That's probably a new word for you that you haven't heard before. So get ready for that. And describe end behavior. We did end behavior already, specifically with polynomials, but it takes on a different meaning here with exponentials. Okay. So, and then we will have a quiz then next class through the homework that we just did. Not anything about this, but through the homework we just did. Right? Function operations, including compositions and inverses. Just those things. So exponential functions, right? The standard form exponential equation is a times b to the x. You know, it's exponential because it's got the variable in the exponent. Right? Now look at all the things that come after that. First, a doesn't equal 0. A and b are real numbers, right? But a does not equal 0, because what would you have if that a equals 0? Okay, well, the whole thing would be 0, right? B does not equal 1, because if b is 1, then you've got 1 to the x. And what's 1 to the x? It's just 1, right? That would just be a horizontal line. And b is defined as being greater than 0. Right? So b is always greater than 0. Now there's going to be two kinds of exponential functions. The first one, when b is greater than 1, is called exponential growth. Right? And b, in that case, is called a growth factor. Okay. Looks good. Okay. So the parent function for exponential growth is f of x, or y, equals b to the x. B is the base, right? B to the x, which means a is 1. If we use the format that I had in the last slide, it's just assume that the a is 1. So all you've got is b to the x power. And b, for exponential growth, I mean, it's going to be some number which is bigger than 1. I'm showing you these two, y equals 2 to the x and y equals 4 to the x, just to make the case that whatever is the base doesn't really matter. You know, if it's greater than 1, it's exponential growth, and it has that shape, which is kind of hard to see a little bit on these graphs. I'm going to step away from the microphone here. But it's hugging the x-axis to the left, and it's going up into the first quadrant to the right. Now, definitely goes up faster if it's 4 to the x instead of 2 to the x, but it's essentially the same basic shape of graph. So if you get a function which is 2 to the x or 4 to the x, those aren't transformations, right? The parent function is b to the x. You got to fill in something. So you wouldn't say like that's a stretch by a factor of 2. It's not. That's part of the function. You got to put something in there. Now your calculators there look better than than what I've got here, because my emulator is for the last version of the 84. You know, yours have color coded, you know, for everything you put on there, you know, it's a different color, and this thing doesn't. You know, this thing makes it look like the graph is actually stopping almost like right there, and it doesn't. It keeps going along the negative x-axis. So again, don't confuse changing the base to being a transformation, because it's not. Okay, here's a little cleaner graph to look at. Right, this is y equals 2 to the x. Okay, and we're going to look at, first, really the first thing we should look at is this concept of an asymptote. So if you use your, with your calculator, go to the y equals, go to y equals and put in, come on, clear, y equals 2 to the x. So we know how to do that, right? We're going to go 2 hat x. And then go to the table of values. Second. Okay, let me do second table set. If yours is not like right there with x equals 0, because people might have been using this last class, the way to change what you see in your table is above where it says window. See that button right there? It says table set. So if you go to second table set and then make that first value 0, the table starts at 0. Now when I go to the table of values, I'm there. And you could see, for if x equals 0, then the function equals 1. If x equals 1, the function equals 2. 2, 4, 3, 8. You just keep raising 2 to 1 more power. But see what happens if you scroll up. What happens to the left of x equals 0, right? As you go -1, -2, -3, -4, -5, the y values keep getting smaller, right? Because I've got 2 to the x. Right? If I plug in 2 to the -1, that's 1 over 2 to the first, which is a half. Right? If I put in 2 to the -2, we got 1 over 2 to the +2, which is 1/4. As they keep going to the left, then the numbers are going to get smaller and smaller and smaller. Now you can scroll up and just see what happens to those numbers. It looks like at x equals -10, they switch to scientific notation in order to show a really small number. And it keeps getting smaller, 10 to the -4th, 10 to the -5th, 10 to the -6th. So, but the question is there anything we could ever plug in for x that would make the function actually equal 0? What happens if I plug in 0 for x? Does that equal 0? Equal 1. Anything that's 0 is 1, right? If I put in positive numbers, the graph gets big, right? If I put in negative numbers, I just keep getting these fractions that are, smaller and smaller and smaller. The denominator is bigger and bigger and bigger. But there's nothing you could plug in to ever make that actually touch. So when that happens on a graph, then that line, which is getting closer and closer and closer to, is called an asymptote. Right? That's the word that's on the screen right there. Asymptote. Right there. Now normally, if you have an asymptote, you draw it in like a dashed line. Something like this. That was not good. And then you label it. What's the equation of that dashed line? It's a horizontal line, so it's got to be y equals 0, right? That's the asymptote. So the graph is going to get infinitely close to that line, but it can never touch. There's nothing you can do to make it have y equals 0. Okay? So the domain of an exponential function is all real numbers. There's nothing that you can't plug in. There's going to be no issues, divide by zeros, square roots of negatives. It is going infinitely to the left and infinitely to the right. The range is y is greater than 0. It's not or equal to because it can't touch that line. Y is greater than 0. the horizontal asymptote is y equals 0. And then the end behavior to the left, as x approaches negative infinity, you're going towards the left. The graph of the function is getting closer and closer and closer to the line y equals 0. So you would say that as x approaches negative infinity, y approaches 0. Now you could describe an end behavior for the right side of the graph too. Like as x approaches positive infinity, what does it look like y is approaching? Positive infinity, right? But usually if they ask the question about end behavior for this, they're really going to want the side like towards negative infinity, where it's approaching the asymptote. Right? The polynomials, when we did them, they always went towards infinity or negative infinity. Okay, now it's going towards some fixed value, at least on the left. Okay, and let's see the y-intercept. Notice where the y-intercept is. It's at 1. It's at 1 because what happens if I plug in x equals 0? 2 to the 0 is 1. Okay, so that's normal. Okay, if the b is less than 1, that's called exponential decay. And in that case, b is called the decay factor. So again, I got an asymptote right here, which I can label. Y equals 0. Now this graph is actually y equals 1/2 to the x. So if the b is less than 1, that's the shape of the graph you get. You know, it wouldn't matter much if you put 1/3 to the x or 1/4 to the x or 3/4 to the x. It's still going to be the same basic shape. Nothing in particular changes because of that. Now, you know, what we're doing right now, they're going to say, because the b is less than 1, this is exponential decay. But you could actually have a different standard for this. 1/2 is 1 over 2 to the first. So if I move that 2 to the numerator, then that becomes 2 to the negative 1, right? 2 to the negative 1 is the same thing as 1 over 2 to the positive 1, which means this is y equals 2 to the negative x. And sometimes that's the way they define exponential decay. It's not because the b is less than 1, it's because the exponent is negative. Right? And in this case, for the end behavior, it's when x approaches positive infinity. As you go to the right, it looks like the graph is approaching that asymptote of y equals 0, so the y approaches 0. It never quite gets there, but it approaches that. No, I don't think I have any. So for exponential growth, if you've had a biology class or some kind of science class, a lot of times when they do population models, trying to show growth, they'll use exponential growth models. And when it comes to exponential decay, if you're in chemistry and you do half-lives, then that's exponential decay. I mean, they're very practical functions. Okay. So use the calculator to graph. So I'm not going to make us necessarily plot all this stuff, but we'll do a little bit of plotting, but not that much. The SOL actually says we should use the graphing calculator to explore the graphs. But you know, this is the way I like to compare things on the calculator. You have a different calculator in your hand right there, but maybe you got an older one at home. Let's say that I want to compare the graph. Let me clear my memory. 712. I want to compare the graph of y equals 4 to the x, because that would be the parent function, to the graph of 1/2 times 4 to the x. So I'll put it as a 0.5 times 4 to the x. Okay, now in order that those two look different here, I'm going to scroll into the left margin and I'm going to hit enter, and that's going to turn that second graph's line to a fat line. So it'll look different. So if I hit graph, there's the first one, and there's the second one. Now they're kind of hard to see, so I'm going to zoom in with the calculator. Go zoom and 2 for zoom in. Enter. There's the first one. And there's the second. So let me snippet that. New. So what did it look? What is the effect of multiplying the function by 1/2? Well, what do we usually call it? What's the word we use when you multiply by a number which is absolute value less than 1? It's a shrink. It's shrink. The graph's going up slower. That's called a shrink. And you could see that it's doing that, right? So this is a shrink, which is what you expect it to do, right? Shrink. Definitely the y-intercept looks like it is the y-intercept, instead of being 1, see here it was on the original function, it was 1, and now it looks like it's at 1/2. I mean, if you plug in x equals 0 for the y-intercept, you get 4 to the 0, which is 1. 1 times 1/2 is 1/2. So that makes sense. So the y-intercept will always be that first number. You know, if you're multiplying, that's going to be the y-intercept. Okay, did multiplying by 1/2 change the domain or the range? Nope, the domain is still all real numbers. And for exponentials, it's always all real numbers. Okay, always. No matter what we do to the graph, the domain is all real numbers. Okay, the range is still y greater than 0. So let's try another one. Okay, so y equals negative 5/2 to the x. What is going to be the parent function? Five halves to the x. Remember, the base is part of the parent function. So we're comparing y equals 5/2 to the x. Right, that's the parent. To y equals negative 5/2 to the x. Okay, what do you think is going to happen when you put a negative in front of it? It's going to flip it, right? It ought to flip it. So let's do that one in the calculator. Okay, clear. This one will be 5/2, that's 2.5, raised to the x. And then this one will be negative 2.5. Oh, should have had the 5 in there. 2.5 raised to the x. Okay, now I graph. I think I'm still zoomed in. So there's the first one, and there's the second one. So exactly as you would have expected, it flips the graph. All right, so let me snippet that one. So it's in our slides. Zoom is the key right in the middle. Okay. So domain is still all real numbers. What's the new range? Right now the graph, it's underneath the x-axis. It's approaching, but it's approaching from underneath. It's still never going to equal y equals 0. So we have to say y is less than 0. You can see the y-intercept was 1 before, now it's -1. Okay. So sketch the graph of the function, include and label the asymptote, sketch the state the domain and the range. So I'm not looking for like a, like where you plot a whole bunch of points. We'll plot a couple points just to get an idea where it goes, but it's more important just like know the function. What does it look like, and how do these factors like the 4 and the 1 and the 3, how are they changing the graph of the function? Okay, so let's see. What should be the effect of multiplying by 4? It's a stretch. If that number is bigger than 1, then it's a stretch. It makes the graph go up faster. What's the effect of subtracting 1 inside the function? Come on, inside the function. We've done this for several different kinds of functions so far. Right 1. No, it doesn't change. It's always the same. How about subtracting 3 after the function? Down, okay? Now, which one of those is going to move the asymptote? The down 3, right? If you take a horizontal line and move it left and right, it's still in the same place, right? But if you move it down, then the whole graph's got to go down. So let me sketch that. See, what are we doing? We're going to go 1 to the right, 3 down. So I need to draw my graph about like this. Okay, so let me put some tick marks on this. 1 to the right. So I should move the asymptote down 3, dashed and red. And then I should label that line always y equals -3. Now, I know the shape of the graph. This is exponential growth, so it's going to be doing this kind of a thing, right? It's going to be approaching the asymptote on the left and going up into the first quadrant on the right. Let's just plot a couple points to see where that is. Right. First point is, how about if I substitute x equals 1, right? If I put in x equals 1, then I've got 2 to the 0 power, which is 1. Anything to the 0 is 1. 4 times 1 minus 3 is 1. Right? So if we put in 1, we go 1. That's 1 point right there. Okay, and then let's find the x-intercept, or the y-intercept. Put in x equals 0. Okay, then you're going to get 2 to the 0 minus 1. That's 2 to the -1. What is 2 to the -1? It's 1/2, right? So 4 times 1/2 is 2. Minus 3 is -1. So at 0, we have -1. Okay, and so this thing should look like this. It's not a very smooth graph, but Okay, last step. What is the domain and what is the range? Domain? All reals. Remember, that doesn't change. And what is the range? Greater than -3, right? Greater than the asymptote. You know, a lot of times you get answers like, y is greater than -2. It's like you don't want to say that it's going all the way down the line, or maybe you put it y is greater than -1 because that's the one you see where it crosses the axis. But remember, all those points as the graph goes to the left that are getting infinitely close to the asymptote, they've got y coordinates that are getting, you know, infinitely close to -3. So it's got to be y greater than -3. Okay. So try to sketch that one. Do the same thing, right? This is going to be what the homework is like too, no matter what the book says. Just sketch the graph, include and label the asymptote, state the domain and the range. Okay. So this is left. This is up. So which one of those moves the asymptote? The +2. So I should draw my asymptote right here. Label it. And then, like I said, we can get a couple points just to give us a little better idea. How about if we plug in x equals -1? What does it equal? Then I get 3 to the 0 plus 2. 3. Okay, how about if I find the y-intercept? So I'll put in x equals 0. 5. So plot those 2 points. Oh, that was a -1. -1, +3, 0, 5. And you know, with those two and understanding the shape, I can sketch that in. So domain is still all real numbers. What is the range? Greater than 2. Greater than the asymptote. Okay, so when you're dealing with, I say exponential growth models, but it's exponential growth or decay. This is the general equation, right? You got an amount of something, you got a function that represents the amount of something. That's the y, right? The a is always the initial amount. The r is the growth rate, or if it was decaying, it would be the rate of decay, right? And that would be, right, a decimal percent. And then the 1 plus r, that's a growth factor. That's assuming that it's growing, right, that the r is positive. Looks like we're all caught up. So here's the kind of problem you can do with that. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. So write an exponential growth model that gives the number n of incidence t years after 1996. So again, here would be the equation, right? N equals the initial amount. What's the initial amount? 2,573 times 1 plus, okay, what is the growth rate? 92%, right? But we want the decimal version, 0.92. And that's raised to the t power. So n equals 2,573 times 1.92 to the t power. Now whatever you do, don't try to multiply 2,573 times 1.92, right? Because they don't both have the same exponent, so they can't put them together. Okay, now how am I going to use that to find the number of incidents in 2003? What's the value of t in 2003? Right? What does it say there? T years after 1996. So it's 7. So in 2003, t equals 7. So you're going to put that in. N equals 2,573 times 1.92 to the 7th. Right? And that you can just put in the calculator. 2,573 times 1.92 to the 7th. 247,000. So it looks like it increased. Did it increase a little or a lot? A lot, right? And that's the thing about when somebody say that something increases exponentially. I mean, they mean a lot. And you can hear that when you're not talking about math or science. Somebody can just use that. They may be wrong and really not be exponential, but they're just trying to get that point across. It's growing really fast. Okay, there's the math. Now, one place where you definitely use exponential growth, hopefully it's growth, is for compound interest. And compound interest is something that will affect all of us sooner or later. Anybody here have like a savings account or something in your name? Okay. You know what kind of interest rate you get on that account? What's that? It's very minimal, okay? So just to make the point, right? Let's just say you have a 12% annual interest rate, but it's compounded. It's what they call compounded monthly. What that means is you don't get like one time at the end of the year, they go calculate 12% of your money and they give you that much money in interest. What it means is after 1 month, they give you 1/12 of that, right? So after the first month, they calculate what's 1% of what you've got in your account, and they give you that back as interest. Now at the end of the second month, they calculate, again, the 1% of what you've got in there. But the 1% now isn't just 1/12 of what you started with. It's 1/12 of what you started with plus that little bit they gave you at the end of the first month. And then at the end of the third month, they do it again, 1%. But again, it's not just 1% of, 1/12. It's of what you started with. It's what you started with, but what you added the next 2 months. So you can see that's going to increase the effective interest rate that you get. That's compounding. And this is a formula for compounding, right? So the amount of money you have after T years is represented by the capital A. P is the principal. Principal means that was your initial investment. R is the annual growth rate, again a decimal percent. N is the number of compoundings per year. So for example, if it's compounded monthly, that's N equals 12. If it's compounded daily, N equals 365. And then t is the number of years. Now, if you notice in the exponent right there, n times t, that means that's the number of compoundings per year times the number of years, which means altogether it's the number of compoundings. So like if you had 12 compoundings per year and you had 2 years, that's 24. Okay. You know, I saw an article the other day on the internet, said I forget what they called it, like they didn't say old people, but it was kind of like that. What do they regret the most? You know, their finances. And it was always, I didn't start investing fast enough. Because if you're going to take advantage of this compounding, you need to like get money in when you're young so that it just sits there and compounds over many, many years, right? If you don't start to save until you're 50 years old for your retirement, you know, it's a relatively short amount of time before you need the money. If you save at 30 years old and you got money that's compounding for 25, 30 years before you need it, that's a lot of money. So you definitely want to, you know, start investing, you know, once you've got your careers going, you start socking money away. So I am going to change this on the fly. We're not going to say 1 year. We're going to say 10 years because 1 year is kind of boring. Okay. You deposit $4,000 in an account that pays 2.92% annual interest, which is probably like even more than your savings account gets, but it's not much. Find the balance after 10 years if the interest is compounded with a given frequency. Quarterly, which is n equals 4, and daily, n equals 365. So let's do this one twice. Okay, the amount for the first one will be $4,000. That was the principal, the initial investment, times 1 plus, okay, what is the R? 2.92, but it has to be the decimal. .0292. Right, divided by the number of compoundings, which they just said is 4, and raised to the NT, so 4 times 10. Now you could simplify that a little bit, or you just put it in the calculator like that, right? Exactly like that. Clear. 4,000, oops, I'm a little bit in the way. 4,000, parentheses, 1 plus 0.0292, divided by 4, raised to the, and I'm going to do that in my head, 40. And it looks like 5,350.73 cents. Okay, that was good. Okay, now let's do the same thing again, but this time it's going to be for 365. A equals 4,000, 1 plus 0.0292 divided by 4 raised to the 365 times 10. Back to the calculator. So I've got to change this 4 to a 365. And then go into the exponent, and now the exponent's not going to be 40, it's going to be 10 times 365, which is 3650. Now it's 5,356. .35. You know, it's still not that much money because the interest rate is like so low. Now, when you get into like you guys are all going to go on and have good careers doing something, right? And when you start having enough money to put into some kind of account, like an investment account and not just like a savings account, you can expect to get, 5 to 10% is not unusual. There's times when, it's been like 12%. I think 3 or 4 years ago it was like 12% in 1 year. So you're not always playing around with these numbers that are like 2.92. It could be much more than that. I think the average is 5%. That's kind of what you expect. Of course, that changes if there's a lot of inflation, then that changes. Okay, so that was exponential growth. Right, now we're going to do a graph for exponential decay. So how do I know that's exponential decay? What, say again? The b is 1/2. Right? Since the b is 1/2, we know this is going to have the shape of the graph that goes down from left to right. Okay, so let's say, let me draw my graph, my axes, solid line, black. Let's say be 1 to the left and 2 down. So I'm going like this. Okay, so which one of these transformations is what is going to move the asymptote? The -2 is moving the whole thing down 2. So that would definitely move our asymptote, so we're going to show that first. And label it. Okay, now let's plot a couple points. See, if I substitute x equals 0, or -1, then what does this function equal? Right, you'll get 3 times 1 minus 2, 1. I mean, here's another way you could do this, right? You could always just go to your calculator and put that function on the first line. Clear. So let's make that 3 times 0.5 raised to the x plus 1 minus 2. And then let's go to the table of values and just take a couple integer values from there. So let's see, I just did -1 and I got +1, and it looks like the y-intercept is -1/2. See that? -1, 1, and 0, -1/2. So let's graph those two. -1, 1, and 0, -1/2. So looking at those 2 points and understanding that the graph has this kind of a shape, I can sketch that in. It should look like it's approaching the asymptote to the right. So what is the range? Y is greater than -2. There you go. So again, make sure that you include the asymptote and label it, no matter what the book says. Right? Okay, so try to sketch that one. Right, so what's the effect of the negative in front? Flip, right? What is the effect of multiplying by a constant greater, absolute value greater than 1? Stretch. What does it mean that the base of the exponential is less than 1. It's going to be decay. That's not a transformation, that's just the kind of function we're looking at. Okay, what does it do to the graph when you subtract 5 inside the function? Right and up. So which one of those moves the asymptote? Up 4. So there's the asymptote y equals 4. Okay, we would have expected, if it wasn't flipped, it would have had this kind of a shape, right? But because it's flipped, now it's doing this. You know, I used the calculator to come up with these two values, 4, 0 and 5, 1, and then sketch this in so it looks like it's approaching the asymptote. Okay, what is the new range? Y is less than 4. Okay, one more and we're done. Okay, a new snowmobile cost $4,200. The value of the snowmobile decreases by 10% each year. Write an exponential decay model giving the snowmobile's value y in dollars after t years. Okay, estimate the value after 3 years. Okay, so we're using that same y equals a times 1 plus r to the t that we saw before. Just in this case, because it's decreasing by 10% a year, that's going to be minus 0.10. So y equals initial amount, 4,200. 1 minus 0.1 raised to the t years. Y equals 4,200 times 0.9 to the t. So every time you add one more year, you're going to multiply by one more factor of 0.9. It'll reduce by multiplying by 90%, you're getting smaller and smaller and smaller. So there's the equation. And estimate the value in 3 years. That would mean y equals 4,200 times 0.9 to the third. Okay, 4,200 times 0.9 to the third. 3,061.80. Now, when things decrease in value with age, right, that's called depreciation. So from like a tax perspective, if you have a business and you own certain equipment, right, and it has a certain value, and then, but you say that it's decreasing in value so much per year, and the tax code probably tells you like farm equipment, probably they tell you like, you assume that it's 7 years or something that it loses all its value. Then you do this calculation to figure out how much value it lost, and then you get to reduce your taxes, you know, because of that amount right there. So it's depreciation. You know, people who have a lot of equipment that you own in a business, you know, they're doing that every year in their taxes. Okay. So that was it. Like I said, the first bullet we'll get to next time when we actually know about logarithms, but the rest of them are about knowing the parent functions, being able to transfer them, transform them, describe restricted, in this case, ranges. When we do logarithms, it'll be domains. We know now what an asymptote is, new thing, and we did a little bit of end behavior. So in this homework, if there's anything that says graph, then do like we did here. Just sketch the graph, include and label any asymptotes, state the domain and the range. I think it does say state the domain and range already. Yeah. Yeah. The pass is gone, so just sign in and out.